This talk is about isotropic source components of events in the 2019 Ridgecrest earthquake sequence. Earthquake ruptures are dominated by shear motions. Many observations show that earthquake ruptures are associated with isotropic radiations, which can dramatically change the local failure processes. And it has important implications for many topics like heat flow paradox, crack versus sleep mode of earthquake ruptures. It can also help to identify small explosions from earthquake shear motions. However, solving the small isotropic components of tectonic earthquakes is a challenging task because isotropic radiations have a small wavelength and high frequency, which decay faster with propagation distance. Therefore, solving isotropic components require dense station coverage that can record high-frequency radiations, provide better focal sphere coverage, and help to solve more accurate material properties and earthquake locations. 2019 magnitude 7.1 Ridgecrest sequence is surrounded by 39 stations within 100 epicentral distance, which records high-frequency seismic radiations and help to provide high-resolution 3D velocity models. Therefore, we use these data to perform automated 3D moment tensor inversion and obtain over 200 full moment tensors for magnitude larger than 3.5 earthquakes. To evaluate the effect of near-field data, we choose three events with the largest isotropic components and the smallest isotropic components. We perform a set of inversions by gradually removing the data from near-field stations. X-axis shows the minimum station distance cutoff. Y-axis shows the percentage of isotropic and CLVD components. When we gradually remove the near-field data, the solved isotropic components decreases while the solved CLVD components do not change a lot. This suggests the necessity of using near-field stations for understanding earthquake rupture processes. There are three general explanations for isotropic radiations: tensor faulting caused by fluid in normal stress regime, ruptures on non-planar faults, and dynamic changes of elastic moduli. For probing the underlying mechanism, we analyze the spatial-temporal variations of the solved isotropic components. Here, figure A and B show the spatial distribution of moment tensors colored by CLVD components and isotropic components. Bottom figure shows the temporal variations of isotropic components along A'. There's no significant CLVD components, and adjacent earthquakes show highly different isotropic components. Between magnitude 6.4 and 7.1 earthquakes, we observe large isotropic components in homogeneous struck-slip stress regime. After magnitude 7.1 earthquake, most events with significant isotropic components are located near the rupture intersections and tips, and the maximum isotropic components decay fast within the 2 days after the main shock. The fluid-induced tensor faulting events cannot explain the observed struck-slip stress regime and the fast decay of isotropic components after the main shock. For ruptures on fault with complex geometry, we may also expect a large CLVD components and the complex stress regime without strong temporal variations of isotropic components. Therefore, these two mechanisms cannot explain some of the observations. The significant isotropic components may be mainly caused by damaged rock fracturing that can create fresh faults, cause large decrease of elastic moduli in the intact rocks at the beginning stage of the sequence. The pronounced isotropic components around rupture intersections and tips can also be explained by the dynamic fracturing for short and thick sources. However, the other two mechanisms may also cause isotropic radiations to some extent. Here are the summaries. We have resolved significant isotropic components, which is hard to be resolved without near-field data. Events with significant isotropic components are located near fault intersections and tips, and occurred at the beginning of the sequence. The significant isotropic components may be mainly caused by damaged rock fracturing. The results highlight the necessity of using more near-field data for better resolving detailed local processes and governing physics. Thank you.